Hello, everyone. Welcome to a new session of our Gamma seminar. Today we have the second part of the course given by Ian Anderson from Utah State University about superposition formulas for differential systems. So Ian, whenever you want.
Okay, well, good afternoon, everyone. Thank you very much for the opportunity to speak again today. Let me begin by apologizing for the going overtime, way overtime on my last lecture. I think I'll try and be a little more careful with my time today. So let me begin by going back to the slide from the last lecture. And in the first seminar, I said this is the goal of the two seminars was to prove or explain the following theorem. And so let me just go over that really quickly. Our starting point is a distribution delta, and we assume that delta is a direct sum of two subdistributions with the property that the Lie bracket of vector fields in this distribution and vector fields in the check distribution stay in delta. And this is what we called a hyperbolic Darboux, hyperbolic distribution. We then talked about derived flags last time, and delta hat infinity is the smallest completely integrable system containing delta hat. And then we impose these two conditions. And these two conditions are the conditions of Darboux integrability. Darboux integrability is a method for finding the general solution to partial differential equations, classically partial differential equations in two independent and one dependent variable. And this geometric constraint here, condition, is exactly matches the classical definition of Darboux integrability in terms of intermediate integrals. So this is the data that we start with. And the conclusions are there's three things. One, there's a distribution V hat on a smaller manifold and another distribution V check on another manifold. In the classical case of PDE of F-Gordon equations like the Liouville equation or wave equation, this manifold would be of dimension 7, this manifold would be of dimension 5, this manifold would be of dimension 5. And then, so this is the first thing you get. The second thing you get is that there's a group action acting on these two manifolds as symmetry groups of these two distributions. And then the idea now is to take the Cartesian product of this manifold and this manifold. So classically, this is a 5 and a 5. Classically, this group action would be a three-dimensional group action. So if we have a 10-dimensional manifold and we quotient out 3 dimensions, we're back to a 7-dimensional manifold. And we can also quotient these distributions. And the claim is you start with your differential equation, you can calculate this data, and then you do this quotient construction, and that brings you back to the differential system that you started with. So in the talk last time, we reviewed basic properties of distributions. We took care of this, we took care of this, and we spent quite a bit of time on how you arrive at these distributions. We call them the Vecchio distributions associated to the Darboux integrable distribution that we start with. And so in today's lecture, we're here, we've got to start talking about how you get your hands on this group, or more precisely, we won't be talking about the group, we'll be talking about its infinitesimal generators. So this is where we have to pick up. So last time we talked about contact systems, we talked about Pfaffian systems, we talked about how you can take a differential equation and encode it as a distribution. And I always use the phrase standard distribution to stand for this construction. We gave a bunch of examples. We talked about various definitions, symmetries, characteristic, Cauchy characteristics, derived flags, and so on. Okay, we gave a bunch of examples of this. I want to remind you of one theorem that we did last time. So theorem will come up again today. Theorem. Let delta be a rank 4 distribution on a 7-dimensional manifold if something is true, something else is true, something else is true. So if 3 things are true, these are statements about the derived flag of delta and its Cauchy characteristics, then delta is the standard DE, standard distribution of some kind of DE, f of x, y, ux, ux, uy, some second order partial differential equation in the plane. And I wanted to stress that this kind of reconstruction or recognition theorem is really a very important part of the classical literature with regards to the kinds of things we're talking about. Okay, we talked about Darboux distributions. We gave a bunch of examples. And so this is where, we talked about our Vasio distributions, V hat, V check. We'll review these again in an example. And so this is where we're gonna start off today with these Vasio vector field systems or these group actions. Same Vasio group actions. Same thing. Okay. Okay, so this is our main goal. This is the main goal for today, to talk about this. Okay, so let me recall our starting point. Our starting point is we have 2 distributions, V hat and V check. They don't have to be the same rank or anything. And they have this property here. This is sort of our hyperbolic property. And then we have these assumptions on the derived flags, that if we take one distribution and intersect it with the terminal derived flag of the other distribution, that's empty. What this says is this can't be too big. Because if this distribution is large, then it's probably going to intersect this distribution here. So for example, if this is a rank 2 distribution, and we're in a 7-dimensional manifold, then the derived flag can't be of size 6, because then just the intersection would be non-empty. So this derived flag can't be any bigger than 5 for this intersection to be empty. But if this derived flag isn't too big, then this means the number of first integrals, which is the number of intermediate integrals, has to be sufficiently large. Okay, so here's step 1. I'm going to need some coordinates here. So let's suppose that our delta hat is spanned by some vector fields x hat, and the distribution delta check is spanned by some vector fields x check. Okay. The first integrals of this, so these are this means x hat of a on x hat on I hat of alpha is equal to 0. Okay. So I can't apply, if I apply these vector fields to these functions, I get 0. So what I want to do is apply these vector fields to the other intermediate integrals or first integrals. So that's this line right here. Take the Lie derivative of those first integrals with respect to that vector field and do the same thing here. Take these vector fields and apply them to those first integrals. Okay. Now, it might happen that you have a lot of these and not so many of these. And so what I want to do is pick some of the first integrals here, a sufficient number, same number as I have vector fields here, and form this square matrix, and then form this other square matrix. And it's not hard to show. I'm not going to do it today, but this data here tells you that this is, and this is the absolutely critical step, that these two matrices invertible. Okay, so completely computational. I hand you a Darboux integrable system. You know these invariants. You go off and you calculate these matrices. Okay. Okay, and now here's the key step. This is such an important step that I like to think of it as the fundamental lemma of Darboux integrable systems. Okay, so on the last slide, I had this matrix A, and I had this matrix B here. They're invertible, so I want to make a change of basis. Take the original vector fields you have and twist them up using this matrix A. Take the, whoops, this should be a check here. Take these vectors here and twist them up using B. Now, we're still going to have U hat of I hat is 0, but now U hat of I check is the Kronecker delta matrix. That's because we put this inverse matrix right here. So we have now that on the I hats, this is 0. On the I checks, it's constant. In particular, it's the Kronecker delta. Same thing is true here. Okay. And as I said, we started off with the vectors x gave me span delta hat. The same is true here. So the u's span delta hat and the u's span delta check. And now the next step is to compute the brackets. So I want to take these vector fields here and bracket them with these vector fields. Where's the answer? Well, because delta hat delta check is inside delta hat plus delta check, I can I know that this bracket is a linear combination of the U hats and the U checks. Okay. Now I want to apply these vector fields to a function, so I just wrote that out here. Plug in a function here, plug in a function in here, plug in a function here, and then remember that the Lie bracket on a function is just this commutator right here. Okay. Then A. Now, look what happens if we take F to be one of the check invariants. Well, if I take this to be one of the check invariants, this term is gone, and this is the Kronecker delta, so I'm left with this thing right here. U hat on an I hat is 0. U check on an F is a Kronecker delta, but the derivative of a constant is 0. So this whole side is 0, so that gives me that these are 0. Likewise, I get M is 0. Okay, so what's the conclusion? The conclusion is that the bracket between these two families of vector fields are 0. And this is almost, I don't know, I've never been able to make a formal proof, but this is almost the defining property of a Darboux integrable system. So it's a distribution, delta, which breaks into two pieces. And you can pick a basis for this and a basis for this, U hat and U check, such that they can commute. And I'll give you a simple example. The simplest example is the following. Take this equation, uxy equals u. This is so-called Klein-Gordon equation. After the wave equation, maybe this is the simplest equation you can think of. This is a hyperbolic system. It's not Darboux integrable. You cannot find at any jet order a pair of commuting vector fields for the U hat and U check. So there does not exist a U hat and a U check such that this is true. And in fact, this system of differential equations here is not known to be Darboux integrable. And it's really hard for me to find an example of a system of differential equations for which this is true, but somehow the thing is not DI. So it's almost if and only if. Okay. So again, we started off with delta equals delta hat plus delta check. These had a basis x hat, x check. We moved to a commuting basis, u hat, u check. The next step is to calculate brackets, iterated brackets. So let's start by calculating the brackets of two hat vector fields. And I'm going to call that S hat AB, and take two check vector fields and calculate their bracket. Okay. And the next step is just keep using Jacobi over and over again. So the first Jacobi is to take a U check vector field and bracket it with this. Well, that's an easy Jacobi exercise. That's 0. So we could say here that the S hats are a symmetry of the S check vector fields. Same thing here. U hat S check is 0. And there's a little bit more work by Jacobi to show that these vector fields commute with these ones. Okay. And now we want to iterate this process again and again. So for example, we might do something like this. We might let S, A, B, C be U hat A, U hat B, whoops. SAB equals U hat A, U hat B, U hat C. And then you might take more iterated brackets and so on. Eventually, that's going to stop. You're going to get a set of maximally independent vectors. And I'm going to call the vectors that I get S hat I and S check I. And so each one of these vectors is an iterated bracket of the U's. Each one of these vectors is an iterated bracket of the U checks. How many are there going to be? How many? There's an easy formula for this. The number of these vector fields is equal to the dimension of the manifold I'm on minus the number of invariants, I hat invariants, minus the number of check invariants. So in a classical case of a 7 manifold, where we have 2 I hat invariants and 2 I check invariants, the number of these S's would be 3. Okay. So this set of vector fields that I've calculated have a bunch of remarkable properties. The first one is, by construction, I can derive the terminal derived flag of delta hat are the two commuting vector fields I started with, and all these S hats. The terminal derived flag for delta check are the vector fields I started with, and all these vector fields S check. The number here and the number here are the same. The next property, so this is property number 1. Property number 2 is that the span of these vector fields are equal to the span of these vector fields. I also should point out that these vector fields Si hat and S hat check are pointwise independent. That's really important. Okay. The next property, property number 3, is just by construction, the U checks commute with the U checks commute with the U hats. So the U checks commute with any iterated bracket. And so we have this property here. The U hat on the the U checks on the S hat is 0. And I'm going to interpret that as an infinitesimal symmetry condition. So these vector fields are symmetries of that distribution, and the S checks are symmetries of this distribution. Okay. The next calculation, property not so hard to show either, is if I bracket two of the S hats together, I get another S hat. Well, that's just a definition of completeness because I took as many brackets as I needed to close up a system. And the structure functions here, a priori, that this could be any function on these C's could be any functions on the manifold, but in fact, these structure, I'm going to call them constants, these structure functions can only be in functions of the I hat invariance. Likewise, if I take these brackets, I'm going to get some structure functions, and the coefficients can only depend upon this. So I want to just stress what we've been doing. What we've been doing is simply trading off properties of, we have two distributions, hat and check, and we've been trading off properties of this, or we've been bracketing vector fields in here with vector fields in here, and we just keep trading off, passing back and forward between the interaction between the two sets of vector fields that we, two distributions we've got. The next step is, and this is written out very carefully in our paper with Feld, Vesio, and myself, you can adjust these vector fields by change of basis. So in fact, the structure functions here and the structure functions here are equal to each other, or maybe equal to each other apart from a sign, depending on how you want to set it up, and are constants. Okay, and so because these are constants now, we can think of the S hats as defining an infinitesimal group action. Okay, and we can think of the S checks as defining an infinitesimal group action. If we exponentiate that, we can get an actual group action acting on our two manifolds. Okay. So the theory gives you that what really the theory gives you is an infinitesimal group action, but many times it's convenient just to formally exponentiate that and think that you have an actual group action. You do, but it may only be a local group action. Okay. So as I said, again, we started off with delta hat, delta check, and now we've constructed these vector fields. They form a Lie algebra, and we'll call that the symmetry algebra of the opposite distribution. And we're going to call the abstract Lie algebra, so the Lie algebra, viewed as an abstract Lie algebra, we're going to call that the Vesio algebra of our starting distribution delta. So it's, again, start with these things, find the U's, find the S's, get the structure constants. That's the Vesio algebra of our distribution. And in our paper with Mark Felds and Peter Vicicilio, we show that this Vesio algebra is independent of all the choices we've made along the way. It's an invariant of the distribution, the Darboux integrable distribution.
Sorry, I just a little question. The name Vesio algebra is something standard literature or something you decided in your work? Because, you know, Vesio algebra it can be used in several contexts with maybe different meanings.
Good point. We call it the Vesio algebra just because we wanted to pay homage to the Vesio's papers. I think 1940 paper, 1942 paper, where he certainly didn't use the method and the terminology here, but he did show that I would say he did take Darboux integrable DEs, and I would say up to the work by Vesio, this was viewed as a theory of compatibility. So you have your equation like the Liouville equation, and the classical method going back to Darboux and Vesio would say, well, to add to this the equations defined by the first integrals. And then this whole system is a system of compatible differential equations, which can be integrated by the Frobenius theorem method. That is to say, this whole system of equations is equivalent to an ODE. So classically, people would say, you see this even in the more contemporary literature, that the method of Darboux is a method of taking a system of differential equations and determining conditions under which it can be integrated by ODE methods, by adding equations to the original equation which are compatible. So in this sense, I always think of classically the method of Darboux as a theory of compatible differential equations. And this is certainly the thread that Cartan picks up in his 1910 paper. And so I feel that, I think my collaborators feel the same way, that Vassio was the first person to take this theory of Darboux integrability and give it a group theoretic interpretation. And so a priori, there's no Lie groups in this theory at all. But by the time you're done with this construction, you're now heading towards a group theoretic interpretation of the method of Darboux. Mark?
Yeah.
Yeah.
You know, one thing I would how I sometimes been thinking about this. You know how when you give like an ODE and you ask, can you write the ODE as an equation of Lie type? So, there's conditions on whether, you can write the right-hand side as a combination of a Lie algebra vector fields, right? I think you guys know what I'm talking about.
Yeah, in that case, yeah.
Yeah, this is a PDE version of that.
Yeah, and this was the feeling when I read your paper. It was some
Yeah,
kind of
it's
version
like
of
a
that.
PDE version of that idea, right? So if you look at the differential system, there are those vector fields which allow you can write the sort of the system in terms of that those Lie algebra vector fields, very similar to how you do it for an ODE. And this is
So
the
we're going to come back and address this question. We're going to talk about this more. Okay.
Sorry to interrupt, Ian. Sorry.
It's okay. It's okay. I think it's a good question. I think the point is a good one, that lots of things get called Vassio algebras or Vassio this or Vassio that. But
yeah,
we simply did it to pay homage to the 1940 and 1942 papers of. You agree with that, Mark?
For sure.
Yeah. Yeah.
Okay, sorry.
That's okay. Thanks, Mark. Is that okay to sort of answer your
Sure.
questions? Okay.
It's very clear. Thank you.
Okay. Okay, so I think that's that. Okay. Okay, so now let's look at a detailed example. And the example I'm going to work is this famous equation, Liouville's equation. And as a cautionary note, it's about the only one you can write down all the formulas for, but in some ways it's too easy. You don't see the full story. You don't even begin to see the full story by looking at these classical equations. So there's this equation, there's uxy equals square root 2 ux uy over x plus y. So it has a historical note. I think it was so Goursat wrote a paper classifying all F. Gordon equations, which were di at order 2. Okay. And there's a list of about, depending on how you count, there's a list of 10 to 12 or 13 different equations, which are Darboux integrable at order 2. And what Vassio did in his 1942 paper is he went through all those equations and calculated what we're calling the Vassio group, or gave the group theoretic formulation for all those equations which are di at order 2. And I just want to stress I think that's one of the main consequences of the work Mark and I have been doing, and some recent work I've been doing with my PhD student, is that you don't get a good feel for the full story of Darboux integrability just by looking at this class of examples. So we'll see that a little bit later. Okay, anyways, it's an example that we can write out in detail. So here's this differential equation. We talked last time about how you code it up as a distribution. We mentioned how you can now write it as delta hat plus delta check. And then you can just get on your computer and take brackets, or in this case, you can do it by hand. You can check that this bracket is back in, satisfies the condition of a hyperbolic system. And last time we looked at delta hat and we calculated the growth vector. It's 2, 3, 4, 5. And here are the two intermediate integrals. And then what we said was, well, let me restrict to the level surface of this. And when I restrict the distribution delta hat to this level surface, I get this distribution right here. And so this is now, I started on a 7 manifold, but I've restricted this subdistribution to its integral manifolds, to the level sets of its integrals. And I get this distribution. This is a rank 2 distribution on a 5 manifold. And because the growth vector is 2, 3, 4, 5, and we suspect that this is a contact distribution. And last time, in the lecture last time, we introduced some coordinates, which explicitly straightened this out. And then, so when I pull back, when I change variables according to this formula, I get that this distribution looks exactly like the standard contact distributions. So we would say that the Vecchio distribution for the Liouville equation is the contact distribution on jet space. I spilled some ink on my paper there. Okay, now let's do our next step. Okay, so again, I've rewritten everything again. Here's our starting vector fields. Here's our invariants. What was the first step? The first step was to take a linear combination of these vectors so that I have commuting bases. So as formulas here are pretty simple. I have to twist x hat 1 with a little bit of x hat 2, and I have to twist this by a little bit here. And as I said, there's an explicit formula, easy explicit formula, no integration, just a little differentiation to get what these coefficients are. So there's no mystery to where these come from. It's completely algorithmic. And then at this point, you get a big piece of paper, and you can, or you can get on your computer, and you can check that the brackets of these vector fields are 0. So I have a commuting basis for the characteristic or singular subdistributions of the Liouville equation. Okay, and now I calculate the S hats. And the S hats are given by iterated brackets. So I have to start with these two vector fields. I calculate that bracket. Now I'm going to calculate an iterated bracket, so I'll keep my U hat 1, but I'll calculate a bracket with this. I get this, and now I get this one here. It's pretty large. Okay. So even in this simple example, the vector fields that you're dealing with are a little bit complicated. The next step now is to analyze the algebraic structure of these three vector fields, and I just got lucky, and as I said, this was some things that happen with Liouville's equation. It's a little simple. I get S1 bracket S2 is S1, S2 bracket S3 is S3. So right away I can see that S hat 2 is defining a Cartan subalgebra. And of course, this is not in the best coordinates basis perhaps, but we can see right away that this is SL2. If I did a more complicated example, and you can find lots of these in our papers, I might get something like this. S hat 1, S hat 2 is I hat 1 times S3 plus I hat 2 times S phi, something like that. I might, in a larger example, when I take this bracket, I might pick up, as the theory says, coefficients, which are functions of the invariance. And then I have to do another change of basis to get rid of these, to get these to be constant. And again, it's 100% algebraic process, completely algorithmic. Okay, so now this was what we would say here is the Vecchio algebra. For SL2 is for Liouville equation is SL2. And more importantly, these vector fields. Oh, here's the other ones. Okay, so here's the check ones. Same kind of formulas. Okay. And now here we are. Here's our Vecchio distribution. And now I restrict the vector fields also to level sets. And I get these vector fields here. And the theory says that these vector fields should be symmetries of those. You can easily check that if you Lie differentiate these vector fields with respect to this, you get combinations of these again. Okay, so it's SL2 preserving the contact ideal, contact system. So that's how much we know up to this point. And I've summarized it right here. Okay. Oh. But there's more information that we need to get out of this. Okay. And in my earlier papers with this, I'm stressing this now because I felt that in some of my earlier papers, this didn't get stressed enough. So I want to say now, if we look in some classical papers of Lie or the more modern paper by Lopez, Cameron, and Oliver, classification of vector field systems in the plane, or vector field systems in R3 preserving the contact system, either way. Lie, as was always done in the classical literature, was working over the complexes, allowing for complex changes of coordinates. And this modern treatment, it was over R. And over R, there are 3 possible SL2 actions. There's this one. I think that's the upper half plane action. There's another action here. And then there's this action here. And this is the projective action, SL2 action on the line.
Hi, just one comment about that, because I have several works about this classification, and as much as I remember, these vector fields are always analytic. The classification is for Lie algebra analytic vector fields. And I remember that I discussed this many years ago when Pavel Winterding was interested in these Lie algebras. And he used to say that something is missing in the classification. And what I found after several years, after unfortunately Winterding's death, is that if you extend to smooth Lie algebras, you can find more than that. Okay, so it's a little bit tricky. But what I found is that at a generic point, every Lie algebra is like one of these, diffeomorphic to that. But if you have at 13 points, for example, with all the vector fields of the Lie algebra has a 0 at a 13 point, you can find new families of Lie algebras. It's tricky. It has to. It's related to stability and things like that, but it's quite. I think that it could be interesting. But okay, and maybe I will let you.
Yeah, should be interesting. Yeah, I think Mark. I think this was done over this was, I'm sure, was this? I
Well,
can't
there's a
remember.
couple. Yeah, so there is the complex version of that for sure. But the
Yeah,
thing is that, you have sort of the transitive case where that you know the answer via sort of classification of the algebras and homogeneous
right.
spaces. And then you kind of know the numbers based on that. Like on a 2D manifold, it's going to be, SL over the reals, it's SL2 modulo those three inequivalent subalgebras, and that's the end of it, right? If it's transitive, there should be
Yeah, if it's
three.
intransitive,
But
yeah, it is
right, so
it is the same. The
there's
trick,
three there. But then over the complexes, because there's only two subalgebras of SL2C, you get two, and that's why it looks like there's two there.
But somehow
Corresponding,
the argument is that there's more than this. Yeah, could you
yeah,
say your comment again, that there's more possible actions?
yeah, there is even in the real line. It's always said that every Lie algebra of vector fields on the real line, it's at a generic point, yeah, up to a change of variable diffeomorphic to an SL2 Lie algebra or subalgebra of it. But if you consider Lie algebra vector fields that are
right,
analytic, for analytic ones, sorry, but if you
yeah,
consider Lie algebra
smooth.
as a vector field, they are smooth, yeah, it's not truth anymore. Indeed, there are certain cases, for example, yes, a vector field that it's smooth but not analytic. Okay, it would be something like the coefficient is e up to -1 and divided by the module of x, in the real line even. You will find there is not a smooth change of variable changing that to any vector field of the Riccati equation, partial x or x partial x squared, because the coefficient and the rank of the function and the Taylor expansion, the first element that is different from zero is in the infinite. So there is no change of variable. So even for a unique vector field, okay, the classification doesn't work. And normally it has no meaning if you are looking for solutions of problems in a generic point. But for example, for stability of differential equations, when you have all these vector fields of the Lie algebra, they vanish at a point and they are not transitive in the action. So you have more Lie algebras. And I guess I don't know. That is what Winterny told me. That is, I have the feeling that this classification is not complete. I think that there must be more Lie algebra. I think that it was about that, but I will never be sure. It's my idea.
Okay.
But anyhow, I don't want to interrupt. Maybe it's a little bit out.
But can it come from a group action is a little bit of a unclear to me, eh?
Okay, so shall we continue and pick
Yeah,
this
sure,
up in
please.
discussions at the end? Yeah, okay. It's okay?
Yeah,
Continue?
sure. Please go on. Go on. Yeah, it's very
Okay.
interesting. Yes,
Okay, so now we have three SL2 actions. We haven't understood the Liouville equation fully until we determine which one of these actions it is. And so one way to do it, well, I gave you the formula for straightening out the Vecchio distribution. It was on the previous page. So we apply this change of basis to our distribution. We get the standard one. Now apply exactly this change of variables to the vector fields I had on the previous slide. So it's these vector fields right here. Apply that change of variables to these vector fields, and you get partial W, W partial W, W squared partial W. There's your SL2 action on the line. And what's all this other stuff? Well, all these other terms are just the prolongation or the lift of this SL2 action on the line up into jet space. Okay, and so we can say now what our summary is, that the Vecchio action is actually the SL2 action on the projective line, and that's it shows up for the Liouville equation. Okay, so let's have we know we want to talk a little bit about Lie equations. So let's have a look at our example. Here's our Liouville equation. Here's our coordinates that we're using, x, y, u, p, q, r, s. This is our 7-manifold. Here's our characteristic subdistribution from a previous slide. Okay, so this is what I did before. I took this thing, I restricted it to a level set. I got this. I made a change of variables, and it became the standard contact distribution. So let's not do that. Let's do something else. I want to go to, I call this intermediate integral. Coordinates. Okay. So the intermediate integrals were x, r minus, it's a little hard to see, 1/2 p squared, y, and t or u at y minus 1/2 q squared. So we have to take these 4 functions, x, r, u, and t, and complete them to a coordinate system. So I'll just do the simplest thing possible. Keep u the same, p the same, and q the same. And now rewrite this system in terms of these first integral coordinates. And I'm going to use for my basis for my vector fields, I'm going to use the derivatives in the invariant directions. That's 4, and I'm going to complete that to a frame for my space by using the S hats. And when I do that, I find a beautiful formula that delta hat is some combination of those 2 vector fields with an invariant or intermediate integral coefficient. Now, as I said, these 3 vector fields, S hat and S check, they are pointwise independent, and the S hats and the S checks have the same span. So if I want, I can think of these 3 vector fields, S hat and S check, as being the right invariant vector fields and the left invariant vector fields on the Lie group SL2. Okay, and so there's a nice formula for the characteristic distributions in terms of left and right invariant vector fields on SL2. And so if I want to think about my differential equation, I can think of my differential equation as this rank 4 distribution given by this vector field, this vector field, this vector field, and this vector field. And now you say, okay, well, this is a bunch of 2x2 matrices, A, B, C, D, with determinant equal to 1. Pick some nice coordinates on pick some coordinates on SL2. Write those vector fields R1, R2, R3, L1, L2, L3 in terms of those. So I could think of this thing as being some, if I like solve for D, I could think of these 4 vector fields as being defined on a 7-manifold with these coordinates. And just that's what I have. So now you can turn it around and start with,
sorry,
excuse me, start with these. You could start with your favorite coordinates for SL2. You could write these down. You'd automatically have a Darboux integrable system, but you'd have, I'll come back to this again, you'd have a very hard time recognizing this thing as the standard distribution for the Liouville equation. Yeah, go ahead.
Just a little question, because I don't know if you said it. This RILA invariant vector field, you're thinking of them like invariant vector fields right and left, but defining different spaces, because in the Lie group there are they span the same distribution, and here they are spanning different distributions, right. Isn't it?
No, no. These things, I think we had it way. Somewhere we had already here. Somewhere we had that the span,
yeah,
of the S hats. Whoops.
because I got a little bit. Okay. Yeah, I think we get the point. Okay.
It's okay?
Yeah. Now it's okay. I go to. Okay. Yes. Right. Thank you.
Okay, so let me just say that again. The span of the S hats equals the span of the S checks. I didn't mention this, that the S hat kills all the invariants. Okay, and the S checks equals 0. And the S checks kill all the invariants. So you can actually think of your manifold now as being, you can really think of the manifold M as now being this group cross R2 cross R2, where the coordinates here are the I hat invariants and the coordinates here are the I check invariants. So you can think of this, if you start off with a 7 manifold with Liouville's equation on it, you can think of this manifold as being this. Okay?
Yeah, sure. I got lost a little bit with a couple of things, but now I pick it up. Thank you.
Okay, I think that's it. Okay, so hooray. We're up to this point right here. Talked about this Vesio group. And then the last part then is to talk about this symmetry reduction here. So this is the last part of the theorem that we have to explain. Okay, so the first part of this is pretty easy. Okay. So let's just do some generalities. So we have a group acting on a manifold M. We'll let mu sub G be the multiplication diffeomorphism. So this is a group of diffeomorphisms defined by the group action. We're going to assume that G acts regularly. That's kind of a bunch of technical conditions, but the main point is this regularity tells you that the space of orbits, this is the space of orbits, or the equivalence class of points under this action. The space of orbits can be given the structure of a smooth manifold. Regular actions are very hard to come by, and so almost always we're starting with some group action and we're cutting out a bunch of points in order to, and we're working just locally. So it's sort of explain things globally, work locally is sort of the mantra that we live by. Okay, and the important thing to note is this projection map is invariant. If I take a point here, move it by the group action, I'm staying on the same orbit, and so I have pi of gx is pi of x. Okay, and so we've talked about symmetries of distributions. This distribution is a G invariant, and that means if we apply this diffeomorphism to the distribution at some point P, we get the distribution at the transferred point G times P. Okay, and then I'm going to define the quotient distribution or the reduced distribution to be a distribution on the space of orbits, and you just push forward the distribution here. You just take the distribution here and push it forward by pi to this. And you say, well, wait a minute, I only know that I can push vector fields forward pointwise. I didn't think I could push forward vector fields over an entire space. Well, you have to use the G invariance here. And so the fact that this is G invariant means, how do I do this push forward? Well, I take a point downstairs, I pick a point upstairs, which projects to it, and push forward the distribution at that point. What happens if I pick a different point to push forward to? Will that be related to my first one by a group element? And so it all works out that this is a well-defined distribution downstairs. Here's the simplest possible example I can think of for, well, almost the simplest possible example. I'm going to work on a three-dimensional space, X, U, and P. And here's my distribution, partial X plus P partial U plus P squared partial P. And I can think of that as the differential equation, UXX equals UX squared. Okay? And I'm going to see that this distribution, and here's my group action. My group action is simply translations in U. And so this distribution is certainly invariant under translations in U. So the quotient space, the projection map down to, here's my quotient space here, my space of orbits. It's parameterized by Y and V, and here's the projection map right here. And if I push forward this distribution, I get this distribution, which of course is the distribution for this equation, Vx equals V squared. And so this is something very easy that we teach in our first course in differential equations. In our first course in differential equation, we might call this reduction in order, and it's an example here of symmetry reduction. Okay, I want to make two remarks. We often see this equation and also in our elementary classes, and we teach our students that, well, this equation is rotationally invariant, so maybe we can try the following ansatz. We can look for solutions of this form. When we plug this in, we get some second order differential equation, something like this. And then we solve this differential equation and we get a solution to this. And this also sometimes goes by the name of symmetry reduction. Maybe in the physics literature, it's called dimensional reduction. But my colleagues prefer to call this method group invariant solutions. Okay. So group invariant solutions are looking for solutions which are invariant under a group. This symmetry reduction that we're talking about today is not the same as this. It's something completely different. Okay, it's different. They're sort of in some sense, they're sort of at extreme versions different of each other. Okay, so that's remark number one. Remark number two is, well, when we take an algebra class or a topology class, there's all kinds of quotient constructions. And the theme in many of those classes is you have a ring, you make a quotient ring, you have a topological space, you make a quotient space. The original topological space is Hausdorff. You want to know if the quotient space is Hausdorff. Well, the same is true now in differential equations. We have this general construction of symmetry reduction. And one of the goals that you want to do is you want to be able to infer properties of this, what the reduced system looks like, from properties like of this. So if you know the growth vector of delta, if you know the quotient characteristics of delta, if you know the Cartan characteristics of delta, Cartan characters of delta, if you know the symmetries of this, so on, and so conservation laws of this, you know everything there is to know about this. How does that information up here transfer to information downstairs? So that's sort of a general program that you want to have good control over, how properties are related to each other. Okay, so now here's a more substantial example. We're going to come to this equation, Liouville's equation, and we're going to start with the Vecchio data and reconstruct this equation by symmetry reduction. So we're going to do something, and at the end, we're going to be at this equation here. So let me recall for you that we had two side manifolds. We had two manifolds, an M hat and an M check. And this was a 5-dimensional manifold, and this was a 5-dimensional manifold. And on that manifold, we had the two Vecchio distributions, which we had identified as contact distributions. So I'm going to not work in the original coordinates. I'm going to work now in the standard coordinates for those distributions. So I'm going to call them, give a little bit for different name, U hat and U check. Oh, maybe not to be confused with the U's and hats before. Here's our standard distribution on this manifold, a standard distribution on this manifold. And the space I'm going to work on is this one. And that's 10 dimensions. Okay. And then the group action that I'm going to use to make my reduction is going to be SL2. Which SL2? Well, we calculated it out explicitly, and we want to take the projective action. So here, my first set of variables is XU, XV, V1, so on. Here is the projective action of SL2, partial V, V partial V, V squared partial V. Prolong it up to this 5 manifold. Here's the same thing again on this side here. And now take the diagonal action. So that's what our general theorems tells us to do. And the diagonal action just means, well, you let the group act here, you let the group act here at the same time, and infinitesimally, that means just take the sum of these two vector fields. So I have this 10-dimensional space, and I have a 3-dimensional free group action. Okay. So let me just remind you that so we're sitting here with M, and we want to work down to the quotient M over G. This has coordinates xi. We'll call the coordinates down here y in the generic setting. What is the formula for this projection map? Well, this projection map is, we said, was an invariant. So just let y be functions of x where these are invariant functions. Whoops, those are invariant functions. Okay. Since we're working infinitesimally, I have to find, so I have Z1, I have Zi dag. I have these 3 vector fields here. I want to solve these system of PDEs. That will give me, I have 3 vector fields. They're acting freely, so that's going to give me 7 invariant functions, and those 7 invariant functions define for me define for me this projection map to the space of orbits. So at first I was kind of lazy, so I just plugged it into Maple and let Maple find the invariant functions. X and Y, no problem. They're invariant. 1, 2, 3, 4, 5, 6, 7. So I just took out what Maple gave me. Those are the 7 invariant functions. I'm going to use those to define my projection map from my 10-dimensional space to my 7-dimensional space. And I'm going to just push forward my distributions. Push forward 1, 2, 3, 4. Push forward those 4 vector fields. And I get this thing right here. So this here is the quotient distribution in terms of some funny coordinates Z1 through Z7. So it's partial Z1 plus 2 Z4, Z5, dot, 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 dot. Well, you get what you get. It doesn't look like the standard distribution for a PDE. But remember, earlier on, we had a theorem, an identification theorem or a recognition theorem that told me when a distribution is the distribution for some standard for a PDE in the plane. And there's various things you have to test. Well, it's very easy to take this distribution, apply that test, and it is the partial differential. This is the partial differential equation for some PDE in the plane. And there are refined versions of that classification theorem that tells me this is actually the PDE, this is actually the standard distribution in weird coordinates for an F-Gordon equation. It doesn't look like it at all, but it is. And so this is one of the problems with this game. You may pick bad coordinates and you can't do the quotient and you can't recognize what you've got. And that's why these recognition theorems are so, so important and so reassuring. Okay, a better way to do this reduction is to say a better way of getting good coordinates is to use operators of invariant differentiation. So operators of invariant differentiation have the property that if you apply them to an invariant function, you get another invariant function. And our operators of total differentiation are such operators. And if I come back and I look at the invariants that Maple spit out, there was a 1 right here, which was a first order. This is a second order. This involves 2 derivatives. This involves 2 derivatives. This involves 3 derivatives. So I think of this lowest order differential operator as kind of a seed invariant. Sorry, this invariant is a seed invariant in the sense that if I apply operators of invariant differentiation to it, I get all the other invariants. So I start off, my invariant functions, I had x and y were invariant. I have this seed invariant right here. I'll differentiate it and get a second order one. I'll differentiate it to get another second order one, and here's the third order ones. And so using these operators now, I'm going to push forward my contact distributions using these coordinates. And lo and behold, right on the button, I get exactly the formula for the standard distribution. Well, I missed by a sign. I got Liouville's equation up to a sign. If I want to fix that, I should come in here and just twist my action a little bit to pick up a sign change. That's not so important. Okay.
Ian?
Yeah.
Ian, are you getting the invariant differential operators just by taking the z hat plus z checks?
Yes.
Applying those vector fields?
Yeah.
Okay.
So that's right here. So this is dx and this is dy. Okay. And so let me just make a comment about that. These were invariant distributions. Because my group action is free, I can actually find an invariant, I can always find an invariant basis of vector fields and a basis of invariant vector, sorry. I can always find a basis for u hat and u check consisting of invariant vector fields. And one of those invariant vector fields will be my total derivative operator, which I'll use to generate. So that's not an accident of Liouville's equation. That's going to happen all the time, that I can always start off with some kind of invariant, and I'm always going to have at my disposal operators of invariant differentiation. That's just coming from, yeah, I always have that. That's not an accident of this example. Okay? Okay, so let's see. I think we're done. Oops. Okay, so I think we're kind of done here. We've explained every single step in our theorem. I think I just have a couple of remarks to make, and then we're done. Okay, in the first lecture, I mentioned Lee's theorem. We have a hyperbolic DE defined on a 7-manifold, rank 4. If the Vecchio distributions are J2 or R, then the equation, whoops, has a 0. Then the equation is the wave equation. Okay. Now here's a new theorem, and you can make as many of these new theorems as you can calculate Vecchio distributions in Vecchio algebras for. Consider a hyperbolic DE defined on a 7-manifold. Suppose the Vecchio distributions are J3 or R. The Vecchio algebra has an abstract Lie algebra, SL2, but the Vecchio action is actually this projective action. So you start with this thing. Maybe it's in horrendous coordinates. You don't know anything, but all this stuff you can calculate. And the conclusion is that the equation is the Liouville equation. So this data here gives us, just like Lee's theorem, but we had to add in some more hypothesis. This theorem here gives you a complete invariant characterization of the Liouville equation. And that's true in general, is that the Vecchio distributions and the Vecchio action is a complete set of invariants for a Darboux integrable system. It solves for us the equivalence problem for Darboux equations. Okay. Here's another example. As I said, I like this equation a lot because it's counterintuitive. You can't guess what's going to happen for this one. You just have to apply the series. So this example, 3RT cubed, is a nice example. You can't just kind of use your intuition. You have to apply all the formulas kind of religiously and see what happens. So although the formulas for delta hat and delta check, I wrote them down in last week. These were very complicated expressions. You get a kind of a big surprise in that the vector fields for the Vasio algebra or the Vasio action for this equation are about as simple as you can possibly hope. It's just partial u, x partial u, and partial y with some other stuff added in. And so if you calculate the commutators of these ones, it's 0. So the Vasio algebra for 3RT cubed is a three-dimensional abelian algebra. Okay. So how do we get such a complicated thing? Well, it's a complicated equation, not because the Vasio algebra was complicated, but because the Vasio distributions that we use to make this quotient are not the contact system, rather it's the Hilbert-Cartan equation. So again, we can have a New's theorem, which is an intrinsic characterization of this 3RT cubed plus 1. Start with a hyperbolic dE on a 7-manifold. Calculate the Vasio distributions. So if we do the calculation and calculate them, we find it's a 2, 3, 5 distribution. To identify that 2, 3, 5 distribution, which is the Vasio distribution, as the Cartan-Hilbert equation, we can either calculate its symmetries or calculate the Cartan-quartic. The Vasio algebra is a three-dimensional abelian subalgebra. Big problem again, there are many three-dimensional subalgebras.
Sorry, Ian.
Yeah.
I'm very sorry, but I think that we should be finished today in some
within
5 minutes. It's a pity because sure.
Okay, let me just end on this note then. Okay, that's good. I'm sorry. Right. We'll stop. Okay, so let me just, in conclusion, come back to for a quick minute to Lie equations. The advantage of this point of approach, you pick the left and right invariant vector fields on a group, is you always get instantly a DI system with prescribed Vasio algebra. What you don't know when you take this point of view is you don't know what the Vasio distributions are. In the classical case, they're always contact, but in general, they might not be. So I'm going to end, let me just end. I tried to do what I did for Liouville's equation. I tried to write the distribution delta hat and delta check for 3RT cubed plus 1 as equations of Lie type like I did for Liouville, and it's not working out. It's just, it just doesn't seem to be happening quite right. So maybe I'm doing it wrong. Maybe my coordinates are wrong. I'm going to leave that as a good project for people to work on. Finally, let me just end. Recent developments. There's a very nice paper that's now on the web, which talks about elliptic Darboux integral equations by Mark and Tom. They're both here. This is really a good paper. It opens up a lot of new areas for a lot of new applications. And it also puts the classical hyperbolic case in a better perspective. And there's another paper soon to be put on the archive in which we use the group theoretic approach to classify Darboux F-Gordon equations at DI at order 3. And we find that there's some serious mistakes in the literature on previous efforts at this classification. Well, damn it, I went over time again. I'm very sorry. That's not good. Thank you very, very much for your patience.
Thank you, Ian, for your nice talk, really. And now we have time for a very short question. One question, please.
Sorry.
No, nothing. So I would like to discuss this more in detail someday. We don't have time now, but I really would like to talk to you about it. So I will send you an email, okay? Because many of the things you did, they are very interesting, and it's a pity that we cannot continue because I would like to know more. Okay, So thank you, everybody, for yeah.
I have a quick remark, if you don't mind.
Yes, sure.
When Ian mentioned in straightening out the bracket relations on the S hat vector field, so so you got the structure constants, the Vesu algebra. That step isn't completely algebraic. You have to solve some. Solve some differential equations. At least, for example, in the Abelian case. And that's one step where the elliptic case is very different. You have to use some new methods that lean into in the elliptic case. We definitely have to assume that everything's analytic and in fact complex analytic. Well, everything's real analytic, and we have to lean into the complex analysis in order to get that step of straightening out the structure constants. Thanks. That's all I want to say.
Thanks, Tom. Yeah, it's a non-trivial paper.
Okay, so thank you very much, everyone, and thank you for your participation. Ian, it's been a pleasure. It's a true pleasure to have you here. And as I told you, I expect that we will have time to discuss this a little bit more.
Yeah, maybe we can include Mark and Tom too in our discussions. Yeah, great.
Yeah, sure, for sure. And okay, there is no time. Please, Xavi, finish the recording.